Hello, my name is John Morgan, and I'm a 2005-2006 Distinguished Lecturer for the Society of Petroleum Engineers. I'd like to talk with you about liquefied natural gas, about LNG. But before I do that, I'd like to thank the Society of Petroleum Engineers and the foundation that has funded this program of lectures. Thank you. LNG, what's happening and why, is the topic of my program. And this is an exciting area. A lot is happening, and there are a lot of very important reasons for why this is happening. But let's begin where LNG produced. This very first picture shows an LNG production facility in Qatar, in the Arabian Gulf. And here we're seeing tremendous activity in the industry and tremendous growth in the facilities to produce LNG. In the middle of that photograph, we see what looks like a distillation tower, but it's really a very expensive heat exchanger where natural gas enters at the bottom and liquefied natural gas leaves at the top of this refrigeration apparatus. This is an expensive business. These projects register on the financial Richter scale. It costs about $5 billion to run one of these projects, $5 billion for all of the facilities from the very beginning of drilling the wells through the transportation to the eventual liquefaction of this gas in Japan or in Britain or America or wherever it's destined for. But first, let's be sure we understand what LNG really is. You'll see here methane, ethane, propane, and butane, the very common constituents of gas. And LNG, over to the left side of this figure, is mainly methane. Approximately 96% methane with very small amounts of other heavier hydrocarbons. And you can see on this image definitions of LPG and NGL, which we commonly use in the industry. It turns out that, in fact, there are two principal types of LNG. And this is important for commerce. We have both rich LNG, and you can see that that could contain 8% ethane. In addition, we've also got so-called lean LNG, which might only have 1.5% ethane. That will become important towards the end of my presentation. But let's look at a large LNG export facility. This is in Indonesia at a location called Bontang. And if you look closely at this image, you will see that there are actually 3 docking areas, 3 loading docks, because of the large volume of shipping transport coming in and out of this particular facility. And on the left-hand side of the image, you'll see storage tanks for LNG. And in the broad area, in the middle, if you will, down at 6 o'clock, if you imagine this diagram as the face of a clock, you'll see the actual liquefaction facilities themselves. I'd like to introduce the concept now of an LNG train. The fact that from gas production at the top, through the various blocks that you can read on this diagram, down to gas utilization on the bottom, we have a series of very distinct steps in this chain of production. The gas comes out of the ground at the top. In the middle, it's being shipped in LNG carriers that cost over $200 million each. And then finally, we see the gas being used in the receiving country, which could be Japan, Taiwan, or the United Kingdom. This next diagram is very important from a concept standpoint. At the very top, on the left-hand side, you see a gas flow of 5,000 million cubic feet per day. That would need a pipeline about as tall as I'm standing, about 1.6, 1.7 meters in diameter. And along the bottom, you see there distances going up to 5,000 kilometers, and that would be typically a distance between London and New York, let's say. And you'll notice that if we're moving very large volumes of gas, long distances, in general, LNG would be the medium of choice. Up in the top right-hand side of this diagram, you see LNG indicated, large volumes of gas going a long way. And of course, to the left of that, you see the word pipeline, which indicates also large volumes of gas, but perhaps not traveling so far. Are there exceptions to this diagram? Well, of course there are. There are exceptions to almost everything. And certainly we can point to some very notable exceptions to this, most particularly Russian gas moving from Siberia into Europe. In that case, we have very large volumes of gas moving long distances, and up in the top right-hand part of this diagram. But in general, this diagram does hold, and the other aspects of this diagram are also worthy of consideration. This is another very important diagram from a concept standpoint. Please look at the left-hand axis where you see the efficiency. And by efficiency here, we mean of the 100% of gas that comes out of the ground, what percent eventually reach the market? You'll see with pipelines, we start at 100%. All of the gas enters the pipeline in the gas field. But then we see that gradual slope as we use energy for compression equipment to move gas long distances. Notice that this one goes out to 8,000 kilometers in distance. You'll notice that LNG begins on the graph at a little above 90%. Where did the other 10% go? And that other 10% was used as fuel for the machinery that's used in the refrigeration and cryogenic equipment in an LNG plant. So please note, we instantly lose 10% of the energy in the gas to run the machinery in an LNG plant. You'll notice some other methods of transporting LNG or energy, transport energy shown in that diagram, such as GTL, gas to liquids, turning gas into gasoline and diesel, and also turning gas into electricity, which is a perfectly viable way of moving energy to the market. So the concepts on this diagram are important. Let's talk a little bit about how this trade has developed in the last 25 years or so, the last quarter century. These projects have grown from 1 MTA. 1 MTA stands for millions of tons per annum, and that is the language of the LNG business. It's not barrels of oil. It's not millions of standard cubic feet per day. It's not normal meters cubed per hour. The language of LNG is millions of tons per annum. And here we see projects from 1 million ton per annum up to 4 or 6 million tons per annum, which would currently be the largest facilities being built in the world today. Others are coming along that will be perhaps twice this size and are about to be constructed. The supplies initially went to Japan, Korea, and Taiwan in the modern age of LNG. There is an earlier time where trade was between Algeria and Europe, and the prospects of trade between Algeria and the United States in the late 60s. But in this age, which began in the 70s, really we see the main activity in the Pacific Basin going to Japan and the countries that are indicated. More recently, in more recent years, in the 90s, we've seen the growth of the Asian trade, but in particular demand for Europe, the USA, and in the Caribbean. Countries such as the Dominican Republic, which are importing gas to produce electricity. Let's look at the industry growth, and let's find the year 2005, 2006, 2007 here, and you'll notice that's the beginning of strong growth. The various lines there project high, medium, and low growth. And nobody really knows how this was unfold, but what we do know is that we're in a boom period in this industry, a period of unprecedented growth, and like all boom periods, we know that that will end at some point. They all do. But at the moment, there's tremendous growth in LNG, and the actual magnitude and the projection of that growth is difficult to predict. LNG, what's happening and why, is the subject of my talk. And I'd like to give now the first example of why is this happening. This image shows the demand for natural gas in North America. And if you look at this carefully, you'll notice that it begins with gas produced in the lower 48. And then GOM stands for Gulf of Mexico, both close in and shallower waters and deep water production. The Rockies themselves, which is where my hometown is, in Denver, Colorado. I live in the Rockies, and that's a major source of gas within the United States. And then we go up into Canada, and you'll see the line for Canada is a very important source of natural gas to the United States. But then above that, you see two higher levels. One is the possibility of natural gas coming from the Arctic. Tremendous costs involved. We'll see if that happens or doesn't. But the more immediate chance of supply to come as LNG from the Middle East, particularly from Trinidad, which is already a major source of LNG to North America. This diagram shows some yellow dots and some red dots. The red dots are existing terminals to import LNG into North America. You will notice that they are all on the Atlantic coast and none exist on the Pacific coast to service California and the other states in the western area. Obviously, environmental considerations have been a big factor there. In the last few months, down in Baja, California, you'll notice a yellow dot there. That's being turned into a red dot as this presentation is being recorded, and within a year or two that will become an active LNG terminal into North America. In addition, if you look in the Gulf, you'll notice one red dot. There's now a second one that has just been added as an offshore floating unloading terminal for LNG in the Gulf. Let's talk a little bit about gas production, and let's talk about the contract chain. And here you'll see 6 stages in actually developing an LNG project. The very first one is common to all oil and gas activities, the exploration licenses themselves. But then we have an extra step in step number 2, where the gas is sold to the person who's actually manufacturing the LNG. The third step is an agreement of how to spend that $5 billion that we talked about. Several different companies and government organizations will come together to do this, and that will be covered by agreements as described in step 3 on this image. Condensate, which is like crude oil, and LPG production. Those are major sources of revenue in LNG projects. Government, local authority, environmental permitting will always be important in major projects like this. And finally, and most importantly, step number 6, who will buy this LNG? Because ultimately, the recovery of the $5 billion investment will become from the end consumers who pay for that gas, pay for their electricity in their homes and in their businesses. Let's go to Australia, a very important area for LNG production, and look at the North Rankin project. This platform, when it was developed, was the largest gas-producing platform in the world. The company that operates this drilled 13 dry holes offshore before they found gas. This has now turned into an amazing, large LNG production platform, but this is very indicative of the speculative and enterprising nature needed in our industry. 13 dry holes. Let's talk a little bit now about LNG production. And in this very busy and complicated slide, I'm going to ask for you to look at the very middle of this, and we'll see where that 10% of the lost gas went. In the 2 boxes that are outlined and described as liquefaction, we use 10% of the raw gas coming into the facility as fuel for state-of-the-art gas turbine machinery to drive refrigeration compressors to take natural gas from 15 degrees C, from 60 degrees Fahrenheit, all the way down to minus 160 degrees C, minus 250 degrees Fahrenheit. And at that temperature, methane is a liquid that we can load into ships. This diagram all shows much of the technology that's needed to purify the gas and to handle the shipment of the gas to the end user. Let's talk a little about the contaminants in gas. What do we need to remove from gas to make it suitable for liquefaction? Along the top row, water, carbon dioxide, hydrogen sulfide, the usual stuff. Second row begins with sulfur, and you can see the chemical elements shown there, including mercury and sometimes arsenic. But we often have waxes and asphaltenes, and on the next row you see sand, and don't let people tell you otherwise. There is dinosaur dust comes out of these wells also. It's there. We also have lubricants, we have corrosion inhibitors, and we have mystery stuff. We have stuff we produce from the formation, and we don't really know what it is. It contaminates our equipment, it plugs equipment, and many of you will be familiar with these kind of problems in production. We have to remove all of those contaminants to make the gas suitable to be liquefied at these very low temperatures. Here's an example of the dehydration equipment. This is a picture taken in Trinidad. And those 3 vessels remove water from gas to below the limits of detection, below a part per million, down in the part per billion range. Here's a distillation tower, also in an LNG plant, and many of you would recognize this from standard surface facilities. But here's another complicated diagram which illustrates what is currently the leading technology to liquefy methane. All of the equipment along the top is removing those contaminants that I described earlier, the water, the sulfur, the mercury. At the very bottom right-hand corner at 5 o'clock on this diagram is the piece of equipment I described in the very first image that looks like a distillation tower, but which is a heat exchanger that actually does the liquefaction. And over to the bottom left and around 9 o'clock on this diagram is the refrigeration machinery that actually does this liquefaction. Here's another of those expensive heat exchangers, and in a short while we'll look on the inside of this exchanger. Natural gas in the bottom of this, liquid methane out of the top. This is a photograph taken in the Air Products manufacturing facility, which shows a very thin strand of tubing being wound on a very large heat exchanger bundle. These exchanger bundles cost tens of millions of dollars, $20, $30 million to manufacture these things. And it's shown here horizontally, but that piece of equipment is mounted vertically in the two example heat exchangers that we saw earlier. Let's talk a little about the established technologies that are used here. And on the second and third line, you'll see reference to ConocoPhillips and APCI, which stands for Air Products and Chemicals Incorporated, currently the two leading suppliers of technology in this industry. But you'll also see new process technologies described by APCI, by Linde in Germany, by Shell, the DMR, or double mixed refrigerant technology, and also French technology available as Liquefin. All of these technologies are recognized in the industry and used to varying degrees. Let's just take a brief look at the ConocoPhillips technology, also well established in the industry. Again, a complicated diagram, but all the way along the top is gas purification. In the middle are three cascade refrigeration systems, and at the very bottom, you'll see a storage tank where we store the product, the liquefied methane, before it's taken to the market by ship, by marine transport. This is a photograph taken in Trinidad, and up in the top right-hand corner, you can see the empty loading berth waiting for an LNG tanker to arrive. This is Trinidad, and very often that has a ship that's going to be sailing to Boston to unload liquefied natural gas. This also shows the first train at Trinidad. In a very short period of years, there's become 4 trains there, including what is currently the world's largest single train of 5 million tons per annum. So tremendous growth here. And Trinidad is a great example of how an industry could develop in a country very, very quickly and very, very successfully. Let's also talk about an overview of some of the trends in this industry. The first bullet point there you see talks about larger facilities, bigger trains, bigger machinery, economies of scale. That's true for many industries. But you'll also see in the middle of this page the importance of reducing environmental impact with these facilities, reducing the amount of CO2 that's produced as we manufacture LNG, the issue of NOx, nitrogen oxide emissions from the machinery, and finally, these are enormous plants from a cooling standpoint. And their effect on the marine environment of the cooling of the machinery can be very significant. These are all environmental issues that are being addressed and addressed successfully by the industry. Cryogenic gas processing, minus 163 degrees, minus 250 degrees Fahrenheit. That's cryogenic gas processing. And the equipment looks different. This picture shows a valve, just a very common kind of valve, nothing special about it, except this long frost extension. The bottom of this valve will be coated in ice, and we need the frost extension to make sure that the hand wheel that we turn to open and close this valve is also not a ball of ice, so we can operate the equipment. So it's a normal kind of valve, but in the cryogenic business, it has that long extension to make it operable. Here's the facts of life. Here's the unpleasant reality about how you spend $5 billion. It takes a long time. This shows an example project which is 10 years long from the very beginning to the successful completion and bringing this facility into operation. 10 years. A lot can happen in the world in 10 years. A lot has happened in the world in 10 years. So the political risk and just the general business risk associated with these projects is immense. And that's why they're so important to the international financial community. Let's look at the storage of LNG. Let's go to Das Island in the United Arab Emirates and look at an example of a storage tank in the foreground. And you see this very large structure on the top of the tanks. There are no holes or penetrations or connections in the side of this tank, nor in the bottom. And that's for safety reasons. The only way liquid can leave this tank is to be pumped up over the edge of the tank. And that large structure on the right-hand side of the tank is to raise and lower pumps inside the tank itself. Here's a picture of the type of pump that might be used. Now you can really check how high I am. But also you can see how high these pumps are. And in addition, a very typical modern pump would be twice as high as that. This is a single-stage pump. And approximately my elbow in the photograph, you see the orange and red color, that is the electric motor in this pump. That's the electric windings, and they sit inside LNG at minus 160 degrees C. The electric motor is in this cold cryogenic liquid. Very, very interesting equipment, very interesting machinery. Let's talk a little bit about the shipping, and here is interest as well. Let's have a look at the very first ship, the LNG ship to transport LNG across the Atlantic from Lake Charles to Canvey Island near London in England. The project engineer for this ship and its modification is a World War II Liberty ship, a World War II Liberty ship bought and sold twice before it became an LNG carrier. The project engineer on this was a man called Dennis, and he was made to sail with the ship, sailed to England, and Dennis eventually became Sir Dennis Rock and the chairman of British Gas. But he's in his early stage of his career as an engineer, he was responsible for this project. The modern ships look like this. This is an LNG carrier. And I'm going to ask you to look at the letter N on the side of this ship and the white chamfered area above it and then the green deck on the top. We're going inside this ship. And when we go inside, we see this. I think this is a fabulous photograph. I think this is a tremendous image. You see the vertical sides where the letter N was on the side of the ship as I back up to the photograph. You see the white sloped area in that chamfered area at the top and then the very top flat part. This would be full of liquid methane. This is how liquid methane is transported across oceans. This type of construction of the hull and a very large spherical construction are the two standard ways that these ships are built. These are obviously made of alloys, and thermal expansion and so on are important issues in these ships. What's also important is if you remember that previous image that I just showed you, here it is again, and then we look at this image, you can sense that we're looking at one of those tanks and you see some red areas. This is finite element analysis, and particularly those of you watching this video who are involved in your studies and wondering why you are studying finite element analysis in mathematics. Here's one of the reasons, and it's to study the stresses in a hull of a ship like this. When that ship is sailing in a storm, the cargo is sloshing inside the ship. And when that sloshing mass of hundreds of tons of liquid hits the side of the storage container, it produces high stresses. Those are analyzed within the shipping industry by finite element analysis to be sure that we don't get a failure in the ship and in the hull itself. LNG reception. Where does the LNG go? Here's a photograph taken near the capital of Korea, near Seoul, Korea. You see a hole in the ground in the approximately 4 o'clock in this image. That hole in the ground is below ground LNG storage, and the ship that we saw earlier with the N on the side, with the LNG on the side, 1.5 ships would be needed to fill the storage container in that photograph. This is below ground storage, and in the background you'll see some above ground storage as well. We've got to spend $5 billion. We better get going. That's a lot of money to spend. Let's see where it goes. Gas gathering, exploration, drilling the wells, finding the gas, $1 to $1.5 billion. A liquefaction train would cost of the order of $1 billion to $1.5 billion. Ships, $180 million. That price with recent escalation has gone above 200. And of course the regasification facilities themselves could easily be $500 million. Well, there we are, $3.5 to $4.5 billion. Well, I thought you said $5 billion. Well, I did say $5 billion, and these projects are very difficult to control cost-wise, and by the time we've had escalation and all those contracts negotiated, this will cost us $5 billion. Let's have a look at another very interesting photograph. This is one of the world's largest, if not the largest, LNG reception terminals in Japan. Bottom right-hand corner in the bottom, you'll see some more of those below-ground tanks. And up towards 10 o'clock at the end of the peninsula, you'll see a large gas-fired power station where that methane is liquefied and used as fuel for gas turbines to produce electricity here in Japan. It's a very common place that LNG is used. We're moving now towards the end of my presentation. I'd like to talk a little bit more about how the gas is used, how LNG is used. Here's another very important diagram from a concept standpoint. You'll notice here we have summer in the middle of this photograph, and at the left and the right we have the winter months, January and December. And when I say winter, I talk about this from a European and North American standpoint. Obviously, demand for gas is going to be higher in the cold winter months for heating homes and businesses. And in general, it will trend lower when we're talking about gas being used for heating in the summer months. There are some exceptions to this. In Saudi Arabia, for instance, the peak demand for gas would be in the summer months when a lot of electricity and energy is needed for air conditioning and for desalination of water. But in general, we have this trend. This is a problem for us with LNG because we are spending $5 billion and we need to be running these facilities at maximum rate all year, the horizontal lines that you see in this diagram. So we need to have contracts that allow us to export this gas at a very high rate and a constant rate throughout the year and to make our projects immune, to make our project not affected by these kind of seasonal variations. A couple of busy slides here, and ones that you may want to come back to and study later on. First of all, what are the gas markets? Well, you see two bullet points here. The first one is residential and commercial, homes, small businesses, and then the second one is industrial, large manufacturing plants, car manufacturing plants, and other industrial facilities. The main point on these slides is that in the case of residential demand, we don't have any choice but to use gas. If we're set up to use gas in a home, to heat the home in the winter, we generally do not have the option of switching to coal or to oil or wood or any other kind of fuel. Industries, though, will generally set themselves up to be able to burn many different kinds of fuel. A large automobile manufacturing facility could burn coal, it could burn gas, it could burn heavy fuel oil to generate the energy for its operations. That will set a floor price on the value of LNG or gas. If the price for the gas gets too much out of step with coal or oil, it won't be used by industrial customers. So here we see some commercial realities on the business that need to be recognized. Here's another commercial reality that needs to be recognized. This was an import terminal near on the east coast of America, near Baltimore, Washington, that was built in the first wave of LNG projects to import gas from Algeria. At that time, the U.S. government controlled the price of natural gas. And as with many controlled commodities, the country started to run out of gas. On one occasion, an American city, a large American city, literally ran out of natural gas. When that kind of things happen, the laws get changed. The laws got changed to deregulate the price of natural gas, and the people, the company that built this facility, went bankrupt. The business reason for this import terminal went away. You see the jetty in the background. There's an subsea tunnel, actually a tunnel to bring the pipes from that jetty to the shore. This project went bankrupt. It's now being reactivated as an LNG terminal in this current age of LNG, but you can lose money at this game just as well as make money. A little bit more about gas markets, and here's gas markets where we're using actually power generation. This is another busy diagram that is a very important item in the middle, in the very middle of this image. You'll see the amount of carbon dioxide that's produced to produce a megawatt of electricity. You'll notice here that with gas we generate 7 to 8 tons of carbon dioxide per megawatt of electricity. With coal, you'll see that that number is 25 to 27 tons of CO2. And CO2 emission and greenhouse gases and global warming are important topics of our times and of our age throughout the world. And this is certainly an important factor to recognize about the use of LNG. I talked about gas being used to generate electricity, and here we see an amazing machine. We see the kind of machinery that's used as a gas turbine driver to drive an electrical generator in modern power stations. Many of you will own diesel engines and will know that the compression ratio in a diesel engine is somewhere between 20 and 23 to 1. This gas turbine, which is really a glorified windmill, this is just a high-tech windmill, can generate 20 to 1 compression ratio just using axial compressors. It's a tremendous achievement. It's a tremendous machine. And it's indicative of the many fine engineering things that are achieved and applied in this LNG business. Just some quick statistics on this machine. The firing temperatures are above the melting point of the equipment inside this gas turbine. And if we did not have internal air cooling of the blades, the turbine blades in this machine would melt with the temperatures that we're using. Tremendous technology in these things. Please also notice the 60% efficiency at the bottom of this diagram. 60% of the energy in the gas is converted into electricity compared to typically 40% in a normal coal-fired power station. We're getting towards the end of my presentation, and I want to come back now to the issue of not only LNG, what's happening, but why is this happening? This shows an example of the heating values of gases used within Japan at the top, the United States in the middle, and the United Kingdom, Britain in the bottom. Along the bottom is the energy content in megajoules per meter cubed. 40 to 42 on that scale is very similar to 1,000 or 1,050 BTUs per cubic foot. Key thing to notice is there is no overlap between the gas quality used in Japan and the gas quality used in the USA. Florida is an example, but a reasonably typical example of the specifications. What's the point here? LNG that's going to Japan could not necessarily be diverted to the United States if there was a surplus of LNG, because the specifications are different. The Japanese LNG is traditionally the rich LNG that I talked about at the very beginning of the presentation. By contrast, the LNG, or the gas itself, used in America is typically very lean gas, very low heating value. And the reason for that is gas in America is generally processed to remove propane, butane, and ethane for the petrochemical industry. America uses about 17 million barrels a day of oil, but it also produces about 1 million barrels a day of what we call natural gas liquids, propane, butane, and ethane, which are used in the petrochemical industry. That is why we see this big difference of the gas going to Florida and used within the United States compared to the gas that's used in what we call the Pacific Basin, Korea, Taiwan, and Japan. Couple of commercial trends, and there's obviously a lot of them here. A lot of trends here. Number one, LNG costs. In any industry, we're working hard to reduce costs. And in the second bullet point, the issue of risk-taking. In general, this business is built on long-term contracts. But there is some speculative production now being built, not a large amount, and probably it'll never be more than 5 or 10%. But we do see some more speculative, so-called spot production emerging. And the rest of those is a summary, basically, of the trends that are occurring in the industry. The subject of my talk is LNG, what's happening and why. And as I come towards the end now, I'd like to give another example of why is this happening. This describes a situation for gas supply and demand in the United Kingdom, in Britain. The 2 lines on there, I'm going to let you guess which of those lines is the demand and which of those lines is supply. And you'll notice that the gap is growing at a pretty fast rate. As a result of this, the United Kingdom has 3 large LNG terminals, either in construction or now in operation, to bring LNG in the country to close that gap. For those of you who are following the gas supply situation in Europe, I should mention that that supply line on the graph does include the Ormen Lange production out of Norway, which in itself is a very large gas production facility. Even with that gas supply coming to Easington in the United Kingdom, you see that very rapid fall in supply of gas to that market. That gap is the why. That gap is why LNG is happening in the United Kingdom and it is indicative of why it's happening in many other countries. Just a final couple of images here before I close out my presentation. First of all, a world map and world trade. And it looks as though there's arrows going everywhere on that map. Well, that's starting to be the case with LNG. We have the Atlantic Basin from Trinidad up into the United States, the traditional markets from Indonesia, Malaysia, and Australia, going to Japan, Taiwan, and to Korea. But in addition, look please carefully at this diagram at the Middle East. If we look at the Gulf region, particularly of Oman and especially of Qatar, you can see at the moment the traffic going to the Far East, to the Pacific region, but that traffic, as we speak, is now being directed to Europe and to the Americas to supply LNG to both markets. Final image. What are the challenges to this business? The first one, and there are many, this just selects some of the challenges. First of all, permits to import to the United States, primarily driven by environmental problems and environmental issues. Second one is crews for LNG carriers. There are currently a little short of 200 LNG carriers in operation, the ships that transport the LNG. But there's almost another 200 being built or being contracted for as part of this boom. Where do we find the captains? Where do we find the deck officers? Where do we find the crews who are trained to man these trips safely? Tremendous challenge in the shipping business with this growth. The third bullet is the LNG variations. The fact that LNG going to Japan is a different quality to LNG going to Europe and to the Americas. And that does pose its challenges. Security and the safety of these facilities, making them secure, is another issue of our times. And certainly that's an important issue to the LNG industry. And finally, materials and staffing. The engineers to design these plants, the skilled operators to run them safely, the copper, the nickel, the alloys that are needed to build these cryogenic facilities are becoming in short supply as the demand for these minerals around the world grows for many reasons. LNG, what's happening and why? Thank you very much for having me describe this very interesting and exciting area of our industry. And again, I'd like to give my thanks to the Society of Petroleum Engineers Foundation for funding this program. Thank you very much.